This is the video recap for the Balsa Wood Bridge by Brady, Zach, and Andrew. We were tasked with creating a model bridge out of balsa wood that would have to clear a span of 20 inches with a total structure length of 22 inches. One thing we noticed right off the bat is that we would absolutely have to hold 100 pounds, and we would need a ratio of 250 pounds with our strength to our weight, which means if we kept our build at right at 0.4 pounds, we would only need to hold 100. As you can see here, we had a lot of design criteria. Some of the biggest things that were going to get in our way obviously was the amount of wood that we were given. We were only given a few pieces of each type. Some of them were thicker, some of them were thinner, and some of them had varying lengths. We had one sheet that was given to us that was going to be the base of our bridge. And then one big thing that we saw that was going to make it difficult was we needed at least 4 inches of vertical clearance and 4 inches to 6 inches of horizontal clearance, meaning our bridge had to be relatively large. With all of these criteria in mind, we started trying to design our very first prototype. The first design idea was to angle some beams from below the bridge from the outside going in towards the middle. All of this would be done underneath the bridge, and then we could work up from there.
Can either add beams that connect to the top plate in the middle and go out to the corners at the bottom, or stuff that connects in the bottom middle and goes to the corners of the beam. I'm thinking like across this top middle line, we connect diagonal down to the edges here.
After finishing up the drawing for the design, we decided to try to model it out without any glue, seeing what it would look like with the real balsa wood. This is kind of where we ran into the first problem with this original design, is that the angle that we would be using this one beam at was going to be very, very large, basically a 90-degree angle, and it was not going to be able to hold enough weight, or at least we didn't think it would be able to hold enough weight when we applied the pressure. This brought us to design number 2, where we decided to combine a number of different designs onto the bottom of the bridge in order to strengthen the plank.
So here's when we began to start to build our second design. Brady is starting to draw the measurements and everything, and we start building from the middle. We start to build like a kind of diamond formation between the middle, and as you'll see later on, we actually had to cut up the middle because we had to have the hole for the cutout hole. So as we began to place the diamond formation down, as you can see here, we're measuring it. And for each piece, we actually had to cut a different angle. So like on the side there, you can see there's a different angle, and on each sides it was actually opposite angles. Here's where we began to cut the long pieces to support the edge of the diamond so that they would have something to rest on rather than sitting on nothing. We also glued these two pieces together to make a stronger structure, and out of those thin pieces on the side here, you can see there a little bit, we made like a little ledge to sit on the supporting itself. As we began to glue the pieces together, the wood began to warp, so we used clamps and things to hold it down in place. We began to add horizontal and vertical beams to help support the bottom of the diamond rather than just the side of it. Here we also cut out that hole in the middle so we could test the pressure. So here we began to add another supporting diamond just to give those two beams more support.
Here, we started adding horizontal support that reached beyond the original beam. Our first intent was to build above the beam with a triangle-like structure, but because of lack of supplies left, we had to go below. Here we can see that our original beam that we built is on top with the triangle-like structure below. This eventually resulted in a fail because they were not completely connected and they could each move and flex separately. Here we can see our bridge that we built set on top of the test structure. Once some weight was applied, the beam started to split. Where the arrow is pointing, the bottom frame disconnects from the top beam. The top beam starts to flex and eventually it snaps apart from the frame. As more weight was applied, the bridge continued to bend. This resulted in a small weight being held. Okay. The final weight held was 56.3 pounds.
Since we were only able to hold 56.3 pounds out of the 100 required, we weren't able to fulfill the requirement, but we did learn a lot. Our main problem came with not budgeting our materials correctly early on, which led to us having to build the truss structure underneath the bridge instead of on top.